All right, let's continue our discussion on the series stub versus shunt stub matching by exploring the series stub matching network. And all we're going to do is just explore each little piece in isolation. Or I guess we'll start by exploring the load in isolation. Then we're just going to add a layer and then another layer on top of that to see what happens. And we're going to use the Smith chart as kind of a crude visualization before giving the algebraic expressions. So let's start by just imagining none of this stuff exists, and I'm just looking at the equivalent input impedance here without any of this, and there'll naturally be some reflection coefficient associated with that mismatched load, right? So here's my characteristic impedance, and if I ignore this, I just have a signal coming down, striking the load, and then bouncing back again. So naturally, if I were to plot that on the Smith chart, you would just imagine here's my unit circle. Okay, so we'll draw that. And let's hypothetically say, I don't know, the load impedance lands me somewhere here, okay? So it'll be something like 100 ohms plus minus 25J or something like that, all right? So the first thing we're gonna do is we're gonna add some length of line here and just ask ourselves, what is the equivalent reflection coefficient? I'm just going to call that gamma prime. Okay? Now, what happens? Remember, long ago we talked about this. Here is my original reflection coefficient, and if I just add a length of transmission line, and then imagine looking into it here, what happens? So we write this as gamma of D, say, is going to be gamma naught. So I'm going to write, say, gamma sub 0. That's the reflection coefficient that I would have seen here. And I'm going some distance d away. And then you just get e to the minus 2j times beta times d. So if you think about, and that should make total sense, because all that's happening is the signal goes down and comes back again, and there's that phase accumulating in the waves as they go down and back. And that's this term here. So from the perspective of the Smith chart, that just represents rotation in the clockwise direction, negative theta there, okay? As I just keep going and going, this little, imagine this x, as this d increases, it'll just start twirling around and around and around as it gets bigger and bigger. And every half a wavelength is when it'll make one full revolution, right? Because remember, beta is 2 pi over lambda, and so you could write this as, say, 4 pi d over lambda. So every let's say half a wavelength, you get one full resolution. So that factor of 2 would account for the half cycle there. Okay, so basically, just imagine your head as this moves back, this twirls around. Now remember, also we had that magic circle that we thought was really interesting. We do this. Okay. So if I go some distance away, I will eventually land somewhere on that little magic circle. This is the 1 plus jx circle. Or if I keep going and going, I might intersect with it somewhere over here. And remember, this was very special because hypothetically, you could have done something like the following. Let's say I come around to here, right? I have some positive, or we'll do this point here. I am just some distance away. So I'm going to draw this kind of like so. So here is my transmission line. There's some length d. And when I go that length d, let's say I land here on that circle. So I have some negative j reactant or negative reactance here at this circle, but my real part is matched. So what that means is, hypothetically, all I would have to do is add some series inductance here, and then that would take me along this curve to the matched point at the center. Hypothetically, if this was just the right value of L, it would take me to the appropriate. And if I kept on going, I would come around this end of the circle as well. Or hypothetically, if I started here and I wanted to go the other direction, I would not add an inductor. I would just add a capacitor for the negative series reactance. So in your mind, that's exactly what this series stub is doing, because there is some equivalent input impedance looking down here. And that input impedance for an open circuit or a short circuit will be purely reactive. Okay, so as I dial L here, what happens is it just moves me along this circle, either one direction or the other, depending on what the signs will be. I believe, I don't know this off the top of my head, I believe it actually goes clockwise in this case. But we'll look that up and verify that later. But that's the idea. So as I move this length of line here, it's as if I'm adding some inductance here, and it'll just sort of twirl around because remember the impedance here follows that weird fraction of tangents, right? So it's not like some linear relationship between angle and length here, but as you add length, this will just sort of twirl around in weird ways. So that's the idea of a series stub, is it's basically taking the place of this little series reactive element here and just replacing it with a length of transmission line. And what's nice about this little series length of transmission line here is that it followed, instead of following one of these reactance circles, so remember, if I added like a series inductance or capacitor, I would be forced to move along this reactance circle. But if I do a length of transmission line, it moves along the center of the Smith chart. So that circle that I'm twirling around changes when I use a transmission line here rather than a lumped element. So that's kind of the beauty of this series stub matching, is it's essentially taking the place of those lumped elements here using nothing but transmission lines. And the only thing that kind of fundamentally changes the nature of the circles that I start traversing over here in my Smith chart. Okay, so that's the essence of a series stub match. I add some series length D, and I need just enough to get myself from my original point to either the bottom or all the way around to the top, depending on how long I want to make this. And then I add this other length of transmission line here, and because it's in series, that means it will add a reactance, and I'm forced to only go along this circle here. So if I add just the right length here, it eventually will take me down to the origin, and I will have a matched load. So one way to think of this is intuitively is you imagine, there's a signal going down here, it strikes the end and it bounces back, and then I have a signal going down here which strikes and comes back, and then there is some net reflection here where this is going to transmit down and again. And everything is all adding up superpositions. And if you tune these lengths just right, essentially what's happening is these two waves that come together and create a transmission back in the opposite direction, they are destructively interfering. So it's that same concept that we saw with the quarter wave transformer, where you had those signals kind of infinitely bouncing back and forth, and the net transmission back in the opposite direction all just destructively interfered the original reflection from that initial bounce. So this is a similar kind of concept, only you have these two waves kind of bouncing around on each other. But if you get all the lengths just right, they are essentially destructively interfering with that initial reflection, and you get a match at a very specific frequency. So it won't work for all frequencies, but it will have a pretty decent bandwidth depending on your application. All right, so that's the idea of a series stub. So let's move on to the notion of a shunt stub instead.